So in this video, we're going to learn about Cramer's rule. And before telling you what Cramer's rule is, let me show you how to apply it in a specific problem. So that problem is solve for x1 and x2 in this system of equations. You've got two equations here and two variables. This here is an x2. Okay, and we first want to set this system up into matrix notation. And so there we form the matrix A of coefficients, 7, -2, 3, and there's a secretly a 1 there on the x2. So we form this matrix. Then this vector x is this 2 by 1 matrix consisting of x1 and x2, which are unknown at this point. And then on the right here, we've got 3 and 5 in this vector, column vector B. All right, so the first step is form this matrix A sub 1 by taking A and replacing column 1 by B. So B is 3, 5. So we replaced the 7, 3 in column 1 by 3, 5. So that's what the 1 refers to. It refers to which column of our original matrix A did we replace with B. And then the Cramer's rule says that x1 is given by simply by the determinant of A1 divided by the determinant of A. Here's our matrix A1. Its determinant is 3 times 1 minus 5 times -2. That's 3 plus 10, which is 13. The determinant of A also happens to be 13, 7 times 1 minus 3 times -2. And so x1 is 1. What about x2? Well, that's done similarly. Let A2 be the matrix formed by taking A and replacing column 2 by B. So column 2, let's go up and see what A is. Column 2 is the -2, 1, and we're going to replace this by 3, 5. And then our matrix A2 is going to be 7, 3, 7, 3, 3, 5. And then x2, according to Cramer's rule, is simply the determinant of A2 divided by the determinant of A. We've already computed the determinant of A was 13. The determinant of A2 is 7 times 5, which is 35, minus 3 times 3, in other words, minus 9. So that's 26. 26 divided by 13 is 2. And so x1 is 1, x2 is 2. Now those just happen to be it's sort of a coincidence that the index or the subscript here matches the answer there. That's just a coincidence. But what is true in general is you can easily find x1 and x2 at the cost of having to compute a bunch of determinants. Okay, here's what Cramer's rule says in general, is that if you're given an n by n matrix A and also given n by 1 column vector B, and so then essentially what we're given is the system of equations Ax equals B, where x is this column vector like so, then the solution of the system of equations is given by x sub j is the determinant of A sub j divided by the determinant of A, where A sub j is the matrix formed by taking A and replacing column j by the column vector B. So it's exactly what we saw in the simple example on the previous page, and it simply it finds the solutions, but the cost is computing these determinants, and that can be a little computationally challenging to do, but it is a nice result. Here's a problem that uses Cramer's rule but is not a computational problem. And it says, okay, let Ax equals B be a system of n linear equations in n unknowns. So the unknowns are tied up in this column vector x. And suppose it has integer coefficients. So that means that this matrix A is made out of integer entries, and then also integer constants. So that means that this vector B is made out of integers. Prove that if the determinant of A is equal to 1, then this vector x consists of integer entries. In other words, prove that a system of linear equations with integer coefficients such that the determinant of the coefficient matrix is 1 has integer solutions. Okay, well, it follows immediately from Cramer's rule, because Cramer's rule says x sub j is the determinant of a sub j divided by the determinant of a, and then the determinant of a is equal to 1. And then a determinant of a sub j, well, that's an integer, since a sub j is a matrix of integers, because we just replaced a column j in the integer matrix A with column B, and B is made out of integers, and so A sub j is made out of integers, and so taking the determinant of a matrix of integers is an integer by the formula for determinant. Alright, so x sub j is an integer, and that's what we were trying to show. Okay, on this slide we explain Cramer's rule, or the proof. Why does it work? So, alright, we start with this system of equations, ax is equal to b, and we solve for x by multiplying both sides of this equation on the left by A inverse. The benefit that has is A inverse times A is the identity matrix, and the identity matrix times this vector x is just x. And so we get that x is equal to A inverse times B. So this is just like in algebra, except now we're dealing with matrices instead of with single numbers. Okay, and then here's really the key, is that A inverse, we've asserted, but I haven't yet made a video explaining why, that A inverse is the adjoint matrix divided by the determinant of A. So assuming this fact here, we replace A inverse by 1 over the determinant times the adjoint matrix of A. So that's an n by n matrix if A is n by n. And then we have B is an n by 1 column matrix. And so then when we do the multiplication, we're going to get an n by 1 column vector or column matrix. And so I want to extract, so that's what x is going to be, and that's good. And I want to extract the j term of x, so x sub j. And so that's going to be the j comma 1 element of this product. And going back to how products of matrices are defined, they're given by, if I want the J1 entry, I take row J of the first matrix and dot it with column 1 of the second matrix. Now here B has only one column, so okay. And so I've succinctly expressed that dot product in using the summation notation, which says let k range from 1, 2, 3, all the way up to n, and then take these entries of the adjoint matrix that form row j, because j comma 1, j comma 2, j comma 3, that's row j of this adjoint matrix, and multiply them with the entries b1, b2, b3 of the column vector b. Okay, so that's what we have so far, is that aj is equal to this expression here. Now remember, the adjoint matrix is the transpose of the cofactor matrix. So if I take the cofactor matrix and the jk entry of the adjoint is, I swapped the positions here, so it's kj. That's again what the transpose does, is it switches the indices. Okay, then what we have next is that the cofactor matrix was -1 to an appropriate power, given by the k and adding the k and the j, times the determinant of the matrix you form by taking the matrix A and deleting row k and column j. And now I've written out in detail what this sum is. So it starts from k equals 1. So I substitute k equals 1 to get m11. This bk turns into b1, and these are being multiplied. Oh, also this k turns into a 1 here. Okay, so this is some expression. And then now in the next term, k is 2. So again, this notation means k starts at 1, then goes to 2, 3, 4, and stops at n. So now k is 2, so this k turns into 2 here, a 2 there, and the 2 there, and dot, 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 so on and so forth, until k becomes an n. and these all turn into n's. Okay, and so then if you think about what this expression is, this is exactly the expansion by minors along column J of A sub j. Remember, A sub j is the matrix that's formed by taking A and replacing column J by the column vector B. And if I expand by minors along this column, the determinant of A sub j is what I'll get, because I get B1 times the minor associated to the row 1 column J position. That's where I eliminate or delete row 1 column J, take the determinant of the resulting minor, multiply it by the appropriate sign. And then expanding to B2, it's going to be B2 times delete row 2 column J, take the determinant of what's left, that's exactly this, multiply by the appropriate sign, and so on. So this entire sum becomes determinant of A sub j, and that's exactly what Cramer's rule says, is that x sub j is the determinant of A sub j divided by the determinant of A.